All right, good afternoon, everyone. Um, just,
Good afternoon, sir.
yes. Before we get started, I'd just like to find out if you had difficulties with the assignment that I gave you last time. Anybody had any difficulty?
Yes, sir.
Yes, sir. The difficulty, the last one, sir.
What about it?
I didn't know how to. Honestly didn't know how to start it, sir.
Okay, I'm trying to remember what it looked like.
It was the one with the three phase, sir.
Oh, okay. No, it's not as bad, enough. It's not as bad. The voltage between the phases, you'd agree that could be represented by a source, no?
Yes, sir.
So you'd have two voltage sources there, which would have given you the line-to-line voltage. And if you think of those as voltage sources, then you just go ahead and write two mesh equations.
I didn't think of that, sir.
That's all right.
Sir,
Yeah.
I did it, but this is my thing. I did it with one of the sources pointing up into the down, and well, in both instances. In one instance, the current actually balance out back to zero, the addition of all of them, and the other one didn't balance out. So I am wondering if
When you say
'cause
balance out to zero, is it that you're looking at all three phases at the same time?
No, sir. I just used the two line-to-line voltages, but I did it by trial and error, as in I tried the source pointing in both directions on one side, but I would like to know how to actually know which direction the sources are pointing before doing trial and error.
All right. Use what I just said in terms of you're dealing with two meshes. Write the mesh equations and attempt it again. The voltages would have been given based on one phase relative to the next.
Right. Yes, sir.
Yes. So based on that, and you would have understood the theory that if we are going into the positive, then of course it will become minus. And if we are going into the negative, it's plus. So I want you to try it again.
No, so that's what I did, sir. I tried it both ways, and one didn't pan out. but
Okay.
but I know which way is the right way. But I don't really know why. But as I say, I'll try to see it.
All right. I'll give you another 2 days to look at it, and then we look at the solution on Wednesday. But I'll give you another day, sorry, to look at it, and then we'll go through the solutions.
All right, sir.
Okay?
Yes, no problem.
All right.
Yes,
Good.
sir.
So, as I indicated last time, today we'll be looking at two-port networks. Now, I'm telling you before we start, and it's almost a similar thing I said when we started network one. The stuff that we are going to start with, very simple, can border on being very boring. But if you don't understand these very basic principles that I'm going to get into, then you're going to run into problems with two-port networks. All right. So let us not take for granted anything that is said from here on. So let's get started. Trust you all had a good weekend. You're all well rested. So let's get cracking. So I want to start with some definitions. Some basic definitions as far as two-port network is concerned. Basic principles. So we have been using terminals. Yes. We just want to talk and formally define it. So that terminal is simply a point at which a conductor from an electrical component, device, or network comes to an end and provides a point of connection to external circuits. All right. So your terminal is just that point at which you are going to make connection between two devices or two networks. Yeah. And then we can extend the definition from terminal to talk about what a port is. So we have a terminal, and the port is simply a pair of terminals that will be connecting a network, an electrical network or circuit, to an external circuit. All right. Or if you want it simpler, a point of entry or exit for electrical energy. So you have a terminal, it's just a single point at which you're going to make the connections. And as I said before, we have been using these for quite a while now, but we just want to formalize the definition. Okay? And then you have two terminals together. We call that a port. All right, do we have this? Okay.
Just a minute, sir. Okay, sir, whenever you're ready.
All right, cool. All right, so the fact that we're dealing with two-port networks, it simply means that we're just going to have two pairs of terminals or two ports. Right? So a two-port network, we have one port and port two. We have port one and port two. Right? So your two-port network has four terminals. And there are some conventions that we will be applying to these networks. So one port is for input signals, and the other would be your output signals. Okay. So most of what you'll be working with, most of the devices that you'll be working with in electrical engineering are two-port networks. You have never really, well, up to this point, you may not have placed much significance on this, but that's the reality. Right? You have been working with two-port networks, and so some of the examples of two-port networks. All right, some of the examples of two-port networks. Your transistors, your op-amps. And I made the point here that some of the, yes, there are some networks that will have an additional port, which is used primarily for control purposes. All right. So come back to the examples. You have your transistors, you have your op amps, you have your transformers, your transmission lines. Yes? Now, I deliberately chose these examples because what it highlights is that you're going to be having two-port networks, whether you are focusing, as an electronics or a communication major, and also if you are more on the power side, you're still going to have two-port networks. So two-port network theory is applicable to whichever area or whichever area of electrical engineering that you'll be focusing on. Yes? All right. Now, just to provide some context in a lot of what we'll be doing as far as two-port networks is concerned. Now, we can describe the operation of a network using different circuit parameters, okay? And we have looked at all these parameters already. So we have looked at it, or we have worked with them in Networks 1. So there's nothing for you to fear, all right? So we can describe the operation of the network using various circuit parameters. And if we do that, if we describe the network using these parameters, then we can predict the complete operation of the circuit when we vary the load. Yes? So if I have my network, if I have my two-port network, and let us say this is where I connect my load, and this is where the input is. Yes? Then this being my two-port network, what we are saying is that I can define this network using various circuit parameters. And based on the mathematical model or how I describe the network, when I change this load, when I vary this load, then I will see what impact it will have on the input. Similarly, when I change the input, I can see what impact, I can determine what impact it will have on the load because I have already defined the network. So we would have modeled the network, yes? If you want to call it, created a mathematical model for the network. And having that model, I can then speak to the operation of the entire circuit by looking at, by using that mathematical model in relation to the load and the input. And I can, a simple example. You remember we spoke back in Networks 1 about maximum power transfer. Now, in that, at that time we were looking at the Thevenin equivalent, etc., etc. Now, what we're saying here is that I can also define that amplifier. So this is my amplifier circuit. Yes? And that amplifier circuit, we can have it connected to other stages. So whether we're mixing, amplifying, you name it, whatever other activity we have. But then if we're able to now define that entire system and have a model, a mathematical model for that system, then I'd be able to determine what would be the overall operation when I change the output. Now, the example I have always used is what happens to the system when I change or when I attach speakers of different resistances? How will it affect the operation? How will it affect the operation depending on the input that I have? Will I be getting some distortion if I am shouting in the mic? Yes. Will I get the best output if I use a 6 ohm speaker or a 8 ohm versus an 8 ohm speaker? You know, what are these effects? And that's all we are saying here. We can make these determinations if I'm able to define my network or describe my network. But let us, you know, hold all of that technicality for the time being. So some other basic principles that we need to focus on. There are some standard conventions that we are going to adopt. And these are the conventions. One, at one port, the voltage is always positive. The upper terminal is always positive with respect to the lower terminal. So V1, the voltage at port 1, this will be higher potential than that. At port 2, that's higher than that. The other convention that we need to note is that the currents for port 1, I1 is flowing into the network at the upper terminal. Similarly, for port 2, I2 is flowing into the network at the upper terminal. So both currents are going into the network at the upper terminals. And then where the voltages are concerned, the upper terminal is positive with respect to the lower, or is at a higher potential than the lower. All right? That's how we get to take that down. Okay. Now, there are some standard two-port networks, yes, that we're going to be exposed to. Yes, we have already been exposed to them, but we just want to formalize them for this particular topic. So that we have a T network and a pi network. All right, the T network, as you would have already been introduced, is a star network. Okay, now we call it Y, but of course, if you just press out the top part, you get T, right? So that's your T network. Your delta network, or pi, that would be a delta network. Okay. Now, of course, you must have an input portion and an output portion. And since we're talking about two-port networks, as we said, there must be a pair of terminals. So for the T, that's it. So we get T there, and here we have our pi. So in essence, this would be port 1, and this would be port 2. Similarly, this will be port 1, and this will be port 2. All right, so let's give some better diagrams here. So for your T network, that's your T network. All right, so we have the elements here connected, form a T. And then for your pi network, oh, this is, before we get to pi, this is another point. This is a point that is very important. Which is that if A is equal to B, if ZA is equal to ZB, then the network is considered to be symmetrical. So regardless of what C is equal to, if A equal B, then we have a symmetrical network. If that is not the case, if A is not equal to B, then the network is described as asymmetrical. All right.
Sir, you're gonna tell us what that means, sir?
Huh?
What is the meaning of it being symmetrical?
Well, symmetrical just means that if ZA and that is ZA. So if ZA equals ZB, yes, then if you look at the impedance here, it will be the same as looking at it here. So that's what the symmetric, where the symmetry comes about.
Okay, sir.
All right.
Yes.
And then, you know, if they are not equal, then obviously the impedance from this end would not be equal to the impedance from the other end. Agreed? All right.
Yes, sir.
Yeah, man, no problem. Okay. For the pi network, all right, and we show you what we showed you earlier what the pi network looks like. So here we have Z1, 2, and 3. And as we said that the pi network is symmetrical if 1 is equal to 2, meaning if 1 equal to 2, then if I look at it from that end or from this end, it makes no difference. Okay. All right. Now, the point here, where all business of balance and being unbalanced is concerned. We say it's unbalanced because if the impedance seen going into the upper terminal would be different from the impedance on the lower terminal. And this primarily is of importance for communication circuits. So I'm just giving you this as let's just say valuable information. It's nothing that I'll be testing you on because, as I said, it's primarily something that needs to be considered for communication circuits. Yes, but in terms of what that means for our T and pi network, it's that here we'll have a balanced T. Now, you know that because we had the current going in at the upper terminal, yes? So let us say I1 goes in at that upper terminal. And in this one, I2 goes in at the upper terminal. Would you all agree with me that I1 would be coming out at the lower terminal and I2 would be coming out at the lower terminal on that side? Is there anybody who disagrees with that? Or maybe don't understand that to be true? If you recall when we spoke about the return path, remember that? So if I1 is going in at the upper terminal and I1 is coming out at the upper terminal, what can we say about these two impedances?
They are the same, sir.
Give me something better than that.
They're symmetrical.
No, listen carefully. If I1 is the current, remember, you know, this is, all of this is my network. The current that comes in here, you know, I'm not interested in how it divides and whatever else in the circuit. All I'm saying, if I1 passes through this impedance at the top, all right, if I1 passes through this impedance, all right, and the same I1 is coming back through that impedance, what can you say about the two impedances?
That they're in series, sir?
Absolutely, they're in series. And that's how we define series connected elements. We said that if the current entering one or leaving one is the same current entering the other, then they are in series. So I1 up here and I1 down here, it means that these two are in series. So what we really have is ZA, ZC, and the same thing on this side. You agree with me? So this would be ZA, okay, ZA over 2, and then that would be ZB, and that's ZC. So we get back the T network. So in terms of balance, what we are saying is that the impedance seen on one terminal would be the same impedance seen on the lower terminal, as drawn here on the right. Yes, it is unbalanced because I1 encounters an impedance ZA for that terminal. We know that I1 is the same, would be coming out here. Yes? It's the return path for the upper terminal. Fair enough? But it would not be experiencing the same impedance on this lower terminal. So that's why we say it's unbalanced. But the balanced T network, yes, the balanced T network would have the impedance split on these two, between those two terminals, and also on those two terminals. Yes? And for your pi network, then the balance, to obtain balance, we would have, because whatever current goes in here, let's call that IX. Regardless of what happens to it around here. Because remember now, you know, within the network, or here's my network, if I can still connect something out here. Agreed? I can connect it to another circuit. Regardless of what I connect it to, what you can be absolutely sure of is that if IX is going through Z3 over 2, then IX must be coming back through here. Everybody with me?
Yes, sir.
Yes, sir.
So that is how you balance the pi network. So for the T network, you're going to be balancing the terminal, the upper terminal and the lower terminal, yes, at each port. And then for the pi network, to be that. Okay. And I confess, I've only used it once in the last couple of years, you know. as part of a question, but it wasn't to calculate anything per se with respect to balance. I just indicated that it was a balanced network, and from that, you would have known how to structure the relevant T or pi circuit. Okay. Now, a couple of things I want to talk about, because we have used these terms, and in many respects, we have used them kind of loosely. So we need to get these terms clear in our head. All right. Yeah. So the first one I want to talk about is input impedance. And the input impedance is simply the input voltage divided by the input current. So if I want to find the input impedance of a circuit or of a network, all I need to do is to get a voltmeter, measure what the input voltage is, and use an ammeter, determine what the input current is, and I will know what the input impedance is equal to. And yep, we're talking about whether it is phasor or algebraic. So it doesn't matter if we're dealing with an AC circuit or with a DC circuit, DC network. Yeah. We know that the input voltage divided by the input current will give us the input impedance. Now, if you think about it, and I use the examples that I think most persons would be accustomed to. If you are playing music, whether in a car or at home, if you turn it up quite loudly, then you're going to start seeing the lights on the whatever equipment you're playing it on begin to dim. But then again, maybe I'm just aging myself, because you all play music on computers and all these things, so you're not going to see that. But anyway, assuming we're in a car, you turn up the volume. The higher you turn the volume, you're going to see the lights getting dim. All that is happening is that the louder you play the music, it's demanding more current from the system. So if you change the load, and you're changing that load because the output, that higher volume, is taking more, is requiring more power. So in a sense, you're really changing the loading. Eh? And by changing the loading, the input current is also going to change. So if the input current changes, assuming that the input voltage remains the same, yes, then the input impedance will also change. Everybody agree with that? Now, I've said all of this to get to this point, all right, where there is a particular load value. So there's a particular value of impedance. Yes? So there's a particular load impedance, which when you connect it to a passive network, it produces the same value of input impedance. So in other words, given what we said earlier in terms of defining the input impedance, we said that it's the input voltage divided by the input current. We went further to say that the input current is going to change based on what I am doing with the load. Now, if the input current is going to change, all we are now saying in terms of this particular value of load impedance is that when I connect it to the load, to the output, the input impedance will be equal to that value of load that I connect. All right, and this is a special load value that is that each circuit will have. All right, so it is specific to a circuit or to a network. Okay. Now that value of impedance, that value of load impedance, we refer to it. What do you have this? I know I was waffling along while you were writing.
Yes, sir.
No, sir. Give me a second, sir.
Yeah, man, go ahead.
All right, sir.
Okay, good. Now, this impedance is called the iterative impedance when applied to an asymmetrical network. And how did we define asymmetrical network? In terms of the T, we said that ZA was not equal to ZB. All right? So we call it the iterative impedance. And we have not defined any port as yet. All we have given are the conventions in terms of where the current is flowing, the voltage relative, one terminal relative to the other, etc. So the iterative impedance is going to be dependent on which port or which pair of terminals we select as the input and which we select as the output. So if I am going from left to right, I would have a particular value of iterative impedance. And if I'm going from right to left, then I'll get another value. Okay? And then the last thing we want to say is that if, however, the network is symmetrical, then the impedance is given a special name, and that is the characteristic impedance. I will denote it as Z0. So in summary, there's a value of impedance which is applicable to whether your T network or your pi network. There's a value of impedance which when I connect it to one port, it will give me the same value of input impedance at the other port. This is known as the iterative impedance. And of course, that value, that iterative impedance value, will be dependent on which port I use as the input as against the output. If the network is symmetrical, and as I think it was Adams who asked, if the network is symmetrical, it means that the impedances at the upper terminals would be equal for the T network. And of course, the ones that are vertical would be equal for the pi network. We are saying that because it is symmetrical and the impedance will be the same going from one direction as against the other, then the characteristic impedance would be the same. So it wouldn't matter which port I'm looking at. The characteristic impedance would be the same. All right? So let us just do some, just get some math done. Warm up ourselves a bit. So, diagrammatically, what we have is that, remember now, we are saying that if it is symmetrical, so if it's symmetrical, then ZA equals ZB. So we have ZA and ZA at the top. And because it is a symmetrical network, we're saying if we connect Z0, so because it is symmetrical, it will be Z0, which would be the characteristic impedance. If we connect Z0 to this port, all right, so if we make that connection, then when we measure the impedance looking in, it will be equal to Z0.
And sir, that is if it is symmetrical, right?
Yes, ma'am. We only talk about Z0 for symmetrical networks.
Okay.
Once it is asymmetrical, then we're going to be dealing with we're going to refer to it as iterative.
Iterative.
Yeah. And for those persons who are already in the industry, we give, you'll hear this referred to in different ways. So in one industry, may hear it referred to as a surge impedance. All right. And then we have some other things that we need to define, such as image impedance. But, okay. So, ladies and gentlemen, based on this circuit, we can do what we are all experts in by now. We can write an impedance equation for this. So we know that the impedance looking in is going to be Z0, yes? So the input impedance, by definition, Z in is equal to the input voltage over the input current. Looking in, yeah, so if we're looking in here, then we'd have ZA plus ZC in parallel, in parallel with ZA plus Z0. Everybody agree with that?
Yes, sir.
Yes, sir.
Yes, sir.
All right. So if I now simplify that, I'll have ZA plus, I remember we had ZC in parallel with A plus Z0. So we just use product over sum.
Yes, sir.
All right. Simplify that. So that will be ZA times the denominator, and we add it to the numerator. That's all we have done. And the objective here is to find an expression for Z0, which is the characteristic impedance. So by definition, all of this is equal to Z0. That's what we're saying. Because the input impedance is Z0 under these conditions.
So, sir, how you have Z0 on one side equaling to factors of Z0 again, sir? So, how you trying to find Z0 and also have Z0 in the formula? I'm saying how we going to find Z0 if we have Z0 in the formula as well?
Man, that's not a problem. Remember, you're an engineer, you know, anything is possible. But do you agree?
Sir, that not sound good at all, sir.
Eh?
That not sound good at all, sir.
Yeah, man, things are possible, man. So, do you agree that this is true? Because all we have done, you know, you agree that this is the input impedance. Do you agree with that?
Yes,
Yes,
sir.
sir.
All right. And by definition,
Yes, sir.
we said that when we connect Z0,
The input impedance will be equal
right?
to
When we
Z0.
connect Z0, because we have made the connection, you know, the input impedance would be equal to Z0.
Right.
Right? So that's all we are doing here. So I know saying the input impedance, which is that's the input impedance, yes? We're saying that input impedance is equal now to Z0. Yeah? And so
it makes sense.
so we can now cross multiply and start simplifying. Right? So if I cross multiply, I get that. Yes? And then all I want to do is to get Z0 on the left-hand side. All right, so we have that. So it means therefore that Z0 is equal to the square root of ZA squared plus 2ZA ZC. Okay. Now, everybody have this?
Yes, sir.
Yes, sir.
Yes,
All
sir.
right.
Yes, sir.
I suppose you'll just shout if I'm going too fast, eh? All right. So here what I'm going to do is I'm going to carry out a little exercise here. So we want to short circuit the T network. So I'm just going to short circuit the output terminals. And if I short circuit those terminals, then the impedance would be ZA plus ZA ZC over ZA plus ZC. All right. If I open circuited the terminals, then that would be the expression. So for your benefit, let me just go back to the slide. All right. So here's my T network. And what I'm saying is that if I were to put a short circuit here, if I were to connect that port, the two terminals on that port, good, then the impedance equation would be ZA plus ZC in parallel with ZA. All right. If I were to leave it open, yes, then the impedance would be ZA plus ZC. That's all we're saying, because if you are looking in here, it will just be A plus C if this is open. And if it is closed, then it would be ZA in series with A and C in parallel. All right?
Yes, sir.
Nothing fancy.
Sir, kind of confused at this, sir.
Need me to go again?
Yes, sir. I try to follow. You said if you short out that side, right?
No, I didn't say that. I
If
said
you short out,
circuited.
yeah, there.
That's what we thought. Yeah? So if we short circuited these terminals, and we're looking at the impedance here.
But, yes.
This is no longer under
Oh,
consideration.
okay. So you're saying that ZC would be in parallel with ZA now. Yeah, I see that. All right.
So it is ZA
in
plus
series with
ZC in parallel
with
ZA.
ZA. It's the open circuit part that's I'm not getting.
If I open it,
I see.
if I open it, yes, then the current would only go through A and C and then come back. So it is
yeah, okay.
plus ZC.
Understood. Understood, yes, sir.
No problem, man.
Yes.
All right, so we go back to what we're saying here. So if I short circuit, I have A in series with A and C in parallel. If I open circuit, I have A and C in series. Agreed?
Yes, sir.
Now, if
Yes,
you look at this, all right, if I multiply the open circuit impedance by the short circuit impedance, so I have, if I simplify this, I'll get ZA squared plus 2ZA ZC over ZA plus ZC. So just multiply the denominator here by ZA, then you'll get ZA squared plus ZA ZC. So we get 2ZA ZC. Yes?
Yes.
So these cancel. The ZA plus ZC cancel, and we are left with that. So the open circuit impedance times the short circuit impedance will give us this expression. But if you recall what we just calculated,
Yeah, it look like it.
all right? So the characteristic impedance would also be given by the square root of the open circuit and the short circuit impedances. In other words, if you have a symmetrical network, you want to find the characteristic impedance.
Oh,
Yes? What you would do is to short circuit the terminal, find the input impedance. Yes? Open circuit the terminal, find the input impedance,
and
multiply them and find the square root.
And so this is true for all T networks.
I said, if you're finding the characteristic impedance, all right? So if it's a characteristic impedance, the mere fact that I refer to it as characteristic impedance, what does that tell you?
It's symmetric, sir.
Absolutely, it's a symmetrical network. Good. All right. Now, is there anyone who don't understand what we have done so far?
All right, sir. Could you go over back the or you get the square root of ZO down there? The ZO is square root of Z, the open circuit plus short circuit.
Go again, go again.
Could you go over the last part of the equation, sir? Or you arrive at ZO is equal to the square root of this open circuit?
Usual networks, man. I just cheat. In other words, this is the short circuit impedance expression, yes?
Right.
And this is the open circuit impedance.
That's correct.
I know what I want. So when we simplify this expression, let me take out all of these markings. When I simplify this, I'm going to get this. You agree with that?
Yes, sir.
Okay. And if I multiply that by ZA, ZC, which is what I have here, then all I'm going to be left with is the numerator. So I end up with ZA squared plus 2ZA ZC.
Right.
But if you go back to the previous slide, all right, Z0 was equal to the square root of ZA squared plus 2ZA ZC.
Yeah.
So I just make the substitution that ZO is equal to the square root of Z short circuit times Z open circuit.
Get this, sir.
Huh?
Yes, sir. Understood.
You're good now.
Yes, sir.
All right. Anybody else? Speak now.
Sir,
Okay.
so Sir, the output impedance that you did before, that's for only if a load is output impedance resistor is attached to the across terminals, while this one is if you're not giving any.
No. What we are finding, what we are finding is the characteristic impedance. The first method we used was to apply the definition for characteristic impedance. And what was the definition I gave you?
The definition was that the input is equal to the output because it is symmetrical. And
okay, give me the definition I gave you for iterative impedance. No man, repeat it. I want to make sure you wrote it down properly.
Oh, ZA square plus ZA.
No, I didn't ask you for an equation. I asked you for the definition I gave you. I gave you a definition. You know. How did I define iterative impedance?
Iterative impedance value is dependent on which of the port it is taken input over in output for respective.
You're not writing the notes, man. You're not taking notes. I said the iterative impedance is the impedance which, when you connect it to the output of the circuit, results in the same input impedance. That's the definition. And we went further to say that if
the characteristics impedance.
No, hold on. I'm going back to iterative. I said the iterative impedance is the impedance the output yields the same input impedance. That's what we said for iterative impedance. Then we went on to say that one, the value of iterative impedance will be dependent on which port is taken as input and which is taken as output. And then the third thing we said was that if the network is symmetrical, then this impedance is known as the characteristic impedance. So because we are finding characteristic impedance, we started with a symmetrical network where we had the ZAs at the top. Let's go back there. All right. So we started here. I see I had it in with the red. See down the bottom. This is where we started, you know.
You
got that?
Yes, I have that.
Good. And then we went on to say this impedance is called the iterative impedance. So that's how we defined iterative impedance. Excuse me. And then we ended up by saying if the network is symmetrical, then the impedance is called the characteristic impedance. Since we are dealing with characteristic impedance, we started with a symmetrical network, meaning the two impedances at the top are equal. That is how we define symmetrical network.
Okay.
Good?
All right. Yes, sir. I got it.
Yes,
now.
Okay. All right. So this method that we have here, the first method we used, what we did was to simply apply the definition. And having applied the definition, we ended up with this final expression for the characteristic impedance. But then I didn't give you any definition about short circuit and open circuit. I am now, because I know where I want to go, I am now saying when you take the short circuit impedance and you take the open circuit impedance and you multiply them and find the square root, you will get the characteristic impedance. All right? So we're all on the same page now?
Yes,
Come
sir.
on.
Yes, sir.
Yes, sir.
You
Yes,
sure?
sir.
Don't tell me yes just to make me move on. Mark, I'm moving on, but don't just tell me yes for me to move on. All right. So if you all say you understand it, I want you to derive the expression for the pi network. Go from definition. Or maybe that, yeah, go from definition. It won't harm you. Go ahead. I'll give you 10 minutes on that one. Okay. Okay, so
Sir, I'm wondering if I'm doing something wrong because it looks like I'm coming back down to the same thing as the first one.
going back down to the same thing, you're doing something wrong.
It should. Sir, I'm stuck because I'm a factorization.
Sir,
So
for mine,
this would be the expression. Huh?
sir,
What
for
was that?
mine, I got
Huh?
like where you have on your diagram Z2. I had that as Z1. I had the top one as what I did was Z2 is parallel to Z3, Z3 in series with Z2, and Z2 parallel to Z0. But on my own, I did the numbering different.
So what you had?
I told you I did my numbering different. So I had
Yeah, so
Z1
tell me what you had Z1
bracket
here. No, just tell me
where
where you had.
Z2 is Z1 where Z2 is.
Okay. Okay. That's the only difference?
So the same thing now.
Some ask you said this is Z1, that's Z1. So what did you make this? You made this Z3 or Z2? Up top.
Okay, sure.
Huh?
Just saw my door. So I just saw my error.
Oh, okay.
So,
Right, so
me have Z1, 2, 3. That time.
the equation would be Z1 and no, I'm clicking on your error. Anyway, the equation would have been Z2.
Z1.
Z2. Z2
In parallel with the rest of the circuit.
Z3
In
plus
series with Z2 plus
Z2
Z0.
parallel with Z0.
Yes, sir.
All right. So this is what you're simplifying, and you're setting
Yes.
it equal to Z0.
Yes, sir. Yes, sir.
All right.
Yes, sir, that's sort of, but I got stuck somewhere. I don't know what I did wrong.
Well, it was just an exercise for you to, cut your teeth at. It wasn't anything that you needed to, understand per se. Yeah. No, the key here, however, the key thing that I want to point out is that having done that, what I want you to do, note is that this is also true. The bottom line is, regardless of whether you're dealing with a pi network or a T network, the characteristic impedance will be equal to the square root of the open circuit and the short circuit, the product of that. So again, I want you to take some time, make sure you get that as your final result, and then you apply the short circuit and open circuit and
Sir,
compare it. Yes.
that second part that you just put on there, that is what I was doing, sir.
But
I came up with the same thing.
No, but I told you, I said to you, derive the expression for Z0 from definition.
Oh, I think I misunderstood.
Yeah.
Okay, but I did get back the same thing when I did it.
I get it yet, man. Oh, this you must do.
All right, sir.
Good. All right. So we want to just expand a little more on iterative and add another one to it, which we call image impedance. So the iterative impedance, we have already explained, is the impedance which, when connected to one of the two ports, produces an impedance of the same value in the other port. All right? So we have already established that. So in other words, the iterative impedance looking into port A, if I were to connect that value at port B, then I would get that same impedance at A. That's all we are saying. Similarly, if I'm looking into port B and I connect the iterative impedance for port B at port A, then I'll get the same value. So this is just expanding on the definition that we just gave. Anybody unclear on this?
Sir, explain that again, please.
Yeah, yes, sir. Explain that again, sir.
By definition, the iterative impedance is the impedance which, when connected at one port, yields that value at the opposite port.
Yes.
So if I connect the iterative impedance for port A at port B, then I'm going to get ZA. So if I connect ZA at port B, I'll get ZA.
And that would be the iterative impedance, yes?
Yes. If ZA is the iterative impedance looking into port A. Remember we said earlier, you know, that the iterative impedance is dependent on the port you are looking into.
Yes, sir.
Because we talk about iterative impedance if the network is what?
Symmetric.
Asymmetrical.
Asymmetric, yeah. The characteristic one would be symmetric, yes, sir.
Right? So if it's asymmetrical, it means that the impedance it must depend on which port I'm looking at. Yeah. If it is symmetrical, it wouldn't matter. Either direction I go, I'll get the same Z0 value.
Same, yes.
What do you know?
Yes.
So because it is asymmetrical, what we are saying is that if we look into one port and connect the iterative impedance at the other, I'll get that same value at the first. All right? So it depends on which port I'm looking into. Of course, if the iterative impedance is the same on either side, what does that mean?
It is the characteristic impedance eventually.
It means that the network is symmetrical, and that means we'll have to be dealing with the characteristic impedance.
Yes, sir.
All right. Excellent. All right. So that is iterative impedance. Now, you all draw this already?
No, sir, just a sec.
Hold on, sir.
Sir, quick question, sir.
Mm.
I wasn't at the first part of this class. I'm not sure if you mentioned it, sir. But what kind of circuits would these be implemented into?
Yes,
The
I
whole
did
two-port
mention it.
network.
Right across the spectrum. Almost everything we're doing electrical. Transistors, you name it. Everything. Transformer, transistor, all of that.
And what's the advantage of these types of networks?
You know, reach the say.
All right, sir.
You just it's a matter that you will always have to deal with you'll always be dealing with two-port networks. So there are some principles that we're going to be looking at, some concepts, some parameters that we're going to be looking at how to define it. So you just have to know it.
Okay.
Remember, networks is a tool. You know? Networks is not an end in of itself. It's a tool. All right. So we have now looked at iterative impedance. So let's look at what we call the image impedance. And this one is not as easy, but anyway. So the image impedance, we define it as the impedance which, when connected to the terminals of a network, equals the impedance presented to it at the opposite terminals. Now, here the confusion. But write that first, and then I will give you, or try to give you some clarity by talking about some numbers, right? So if we look at the circuits, that will help us define image impedance. Let's draw this first, and then I'll come back to the definition to try to explain. All right, so try and note the difference between what we just described for the iterative impedance and what we are looking at here for the image impedance. If we look into port A, or if we find impedance looking into port A, when port B is connected to an impedance ZB, yes? We say we have the image impedance if, when I look into port B, I would get the impedance that was connected at that port. Let me try again, because that confused even me. So let me try that again. Let me give you some numbers. All right? Listen carefully. If port B is terminated in an impedance, let us say that impedance is 100 ohms. All right? So I connect port B in 100 ohms. And then I measure the impedance at port A, and I get 400 ohms. Yes? Everybody with me?
Yes, sir.
I
With you.
said,
Yes, sir.
Listen again. I terminate port B in 100 ohms. And then when I measure the impedance at port A, I get 400 ohms. If the impedance seen looking into port B is 100 ohms, when port A is terminated with 400 ohms.
oh, get it, sir.
So we go again. So if I connect port B, so we're talking about image impedance. So if I connect 100 at port A, at port B, and then I measure the impedance at port A, I get 4. I have an image impedance if when I connect 400 at A and then go and measure the impedance at B, I get
I get
100.
100. Yes, sir. I get it. So it's
So
just saying that it's like it's a proof
you're
in
going to
our
try
sense.
simply to go and get in trouble.
But it's like our proof, sir. Say I say if you terminate port B at 100 ohms, and when you measure the impedance at port A, you get 400. You're saying that if you put 400 at A, if you measure the impedance at B, you're supposed to get 100.
Yes.
Understand?
Everybody with me? Now, if the image impedance at both terminals or both ports are the same, then it's a characteristic impedance.
Sir, can I repeat the example that you gave with the 100 and the 400?
So I said if 100 is connected to B, and when I connect 100 to B, I get 400 at A. Then when I connect 400 at A, I'm going to measure 100 at B.
All right, thanks.
All right? Okay. So in this instance, ZB, we would make ZB 100, right? So ZB is 100, based on the example I just gave you. Good? And then I measure. So ZA there will be 400. Agreed? If I then put 400 in the second figure, if I then put 400 at this point, I put 400 here and measure this, it will give me 100. Okay?
Sir, so it's like
And
what's
if
inside
the image
the
impedance on either side is equal, are equal, sorry, then it means that it's a characteristic impedance. Because in other words, it wouldn't matter which side I'm looking at. Yeah, it was Mr. Adams? You were saying something?
Yes, sir. I'm saying it's like inside the two-port network itself, sir. The way all inside of it set up, sir, is like once you're looking at, you're measuring from left to right, then when you're measuring from right to left, it's like a reverse you're doing, sir. That's why it's 400 to 100 and 100 to 400.
Absolutely. So, to wrap up this evening's class, we just take an example. This is the first example for the day. First and only. So take this question from me.
Question, sir.
Mm.
They when I said to determine the image impedance, it's supposed to give you two values. The one at A with along with the one at B.
I'm pretty sure you have to find it, and if them different, then yeah, and if them similar, then it is symmetrical. That's what I'm being saying.
Everybody have this now?
Yes, sir.
Yes, sir.
I just realized I was on mute and I was waxing lyrical. But anyway, um, if we use the principle, yes, that was applied to the characteristic equation, characteristic impedance. Yes? If I make this port, if I open this port, yes, what would ZA OA be equal to?
300.
300.
Two.
Good.
300.
300. These are in series. And then if I short circuit, I'll have 200 plus these in parallel, right?
Yes.
275.
All right, good.
275.
So we'll do that. So we have two open circuit being equal to 300 and the short circuit being 275. So for OA, so if we're looking at OA, we get 287.2 ohms. What do you think?
So far, sir.
If I go from the other port, if I look to the other port and find OB, we're now looking at OB. Same equation, but I'm looking at the open circuit. So looking the other way, I get 400, that's the open circuit. And for the short circuit, I get 300. Yeah, so we get 366.7. Square root, I get 383.
Yes, sir, that's what I have, sir.
All right?
Yes, that's what I have.
Yeah, man. All right. What I want you to do now, all right? What I want you to do for the, I want you to connect. You're gonna find ZOA. I remember how we defined image impedance, eh? So I want
Yes,
you to
sir.
know if the image impedance at OA is 287.2, yes? It means that when you connect 287.2 at B, what would you get?
383 at A.
All right, so do that for me. For the network, you go back to the network, all right? You go back to the network and you want to connect, no, hold on, where am I? I'm sorry, I think I am misleading you. You connect the 383 here, yes? Connect that, calculate ZOA. Connect the 383 there, and tell me what you get.
Sir, I'm gonna get about the same thing, sir.
What did you get?
I got 285.4.
Check your numbers, man, please. Then you're going to connect your 287
Sir,
over
that's
here.
383 at the last thing you just writing.
This is 383.
Okay.
I want you to connect 287 at A and look into B. And tell me what you get.
Get what the same thing.
Yes, sir, I got 287.2.
Okay? And connect the 287.2 and then calculate the impedance ZOB.
Yes, sir. Get 383.
Okay?
Yes, sir.
So that's it for the image impedance. So if you connect the impedance, you'll get what you had calculated at the other end. All right?
Yeah.
For the iterative, we have to do that one from definition. So for verification, that's what we have. All right?
So you can go one slide box, sir, please, sir.
Finish with that already, man. We calculated these already. That's all that's there.
Yes, sir, we did it right, but we just want the verification. We
We
didn't
don't have time for that,
slide
Mr.
mistake.
Wilson. Sorry. So ZOA, we connect the 383 at
Yes,
B,
yes.
and you get 287 ohms. You connect the 287 ohms at A, and you look at B, and you get 383. Okay?
Yes.
All right. And then finally, the iterative impedance, as I said, we go back to the definition. So ZA, if we're looking at A, yes, if we connect ZA at the output, we'll get ZA at the input. So we write that expression. Write the mathematical expressions for these, our impedance equations, yes?
So the first one would be 285.4.
I don't know. That's a slide away. I don't know. I 285 point what?
44.
Huh?
285.44.
Something like that. All right. So for the first one, that's our expression. And of course, you're going to end up with a quadratic, but one of these values will be negative. Eh? So you get 285.4.
Sir, could you go back one side, Mr. Diagram, please, sir?
The same network that we had before, you know. The original network,
Yes, sir.
it's the same network. So it's a 200, 100, and 300. It's a T network. 2, 1, and 3. So first we are connecting ZA at port B, and the impedance seen looking in is ZA. Second network, we are connecting ZB at port A, and the impedance seen looking into port B is ZB. Okay, so for the next one, looking at port B, we look at port B. Remember, we are connecting ZB at port A, and we're looking into port B. Yes? So if we do that, then that would be our expression. We simplify, we get ZB to be equal to 385.4. What you can do as an exercise is to just connect the impedances and work it out as a regular circuit. So you put in the 385. All right, so this will be 385. This would be a 300. This would be a 200. That's your 100. We're saying just find the impedance, seeing looking in here. And do the reverse for the other one. And this is just to, just to build your own confidence in terms of what we have been doing.
Sir, that's the method I used originally.
Hmm?
So I'm saying that's the method I used originally.
Okay. All right. So that's it for our first lesson on two-port networks. All things being equal, on the meet on Wednesday, I'll give you some direction as it relates to the assignment you got last Wednesday. All right. You look back at that three-phase circuit. It's not as bad as you think. And then huh?
Sir, I got disconnected, sir. That's why I was saying, I was asking even from the start of the class if you could send out the video. So I have kind of clueless, sir.
Video for what?
Last week class, sir. The last class.
The video for last week, Monday, has been available since Monday.
No, man.
Is it on the same?
Last week Wednesday class I'm
I
talking.
repeat myself ad nauseum. It was a tutorial. We sat there looking at the screen sometimes for 15, 20 minutes.
No, I'm saying I got disconnected after about 45 minutes in. I knew that was going to happen because I was
Just
using
consult with a colleague to get the items. That's at most that you're gonna get from those videos from that class.
Okay, sir.
Okay.
Sorry, the video for last class is available on the same YouTube channel.
Yeah, it's in the messages.
Okay,
Yes,
sir,
it
thanks.
is. All right, cool. All right, that's it. As I said, next time we look at some parameters, two-port parameters, and just how we use them to define the operation of our networks, and then how we use these parameters in circuit analysis. All right. There be nothing further for me to.
Sir, quick question, sir. This video will be posted, sir?
Maybe.
Okay, sir. I like to be posted, sir. Just to go back and check certain things.
So we would love a lot of things in life. All right. Have a good evening.
Thank you, sir.
All right. Good.